Okay, so I'm Peter Denno. I'm a researcher at the National Institute of Standards and Technology. And I'm going to be talking today about a project that I've led for the last year in manufacturing, smart manufacturing modeling methodology. And I'll give you a sense first of what I mean by modeling methodology in smart manufacturing. And then we'll go into some detail about little sub-projects I'm doing in the process. So, a smart manufacturing system is a manufacturing system. It's a production facility, factory, call it what you will. What's new about initiatives such as smart manufacturing, and there's a couple of them, is the ability to adapt quickly to changes. Okay, so that's enabled by inexpensive sensors, data analytics, and Internet of Things. So smart manufacturing is a government-sponsored program in the United States. Germany has something similar called Industry 4.0. Theirs is probably a little bigger than ours. We have, in the US, we have other programs too. We have the Digital Manufacturing Design Innovation Program, which is supporting some of the same ideas. So at NIST we have what we call programs, and those are these things here, programs. Each program has some number of projects, and the projects have 3 to 6 people in each project. It will have 1 or 2 university grants or contracts and some industrial relationships. So we have work in additive manufacturing, robotics, and we split the pure smart manufacturing work into operations, planning, control, and systems. So my project is this one right down here. So I'm going to only talk about a little bit of this, but there's all kinds of opportunities right now at NIST in these areas. And we work closely together. I work closely with some of these guys over here, some of these guys over here. Okay, so let me talk just about the project now. Off to the left here, I have a list of 20 or so impediments to manufacturing. What is it that keeps manufacturing from being agile? And frankly, the first 2 account for probably 80% of the causes: poor manufacturability and the unavailability of resources. So you have the manufacturability issues and operations research, OR kinds of problems. So this is a slide about our role as people doing research. So we're not so much into building industrial strength tools, but we'll build tools. I like tools. As a means towards getting the ideas and illuminating the requirements in doing this kind of work. And then hopefully industry picks up. We work with industry on developing stronger tools. So modeling methodology for smart manufacturing was going to embody a large body of knowledge. Right? There's ideas from design engineering, system engineering, side of physical systems, operations research, and so forth. That you need a number of these things. We cover a lot of ground. So I think systems engineering in particular is important because there's so much nice research in engineering and design and modeling that could be applied in manufacturing. Of course, it's been applied for many years. But this slide is trying to emphasize the idea that it's applied differently in manufacturing and design. Now, in design, typically, this is the 100,000 meter level here, but you start from requirements and take one pass through to specifications. Right? There's a mature tool chain associated with doing design. Not so much the case in manufacturing. Here, I view the problem and the use of analytical tools as part of the control system. Okay? So manufacturing isn't this one pass thing, but there's an ongoing need. Back here's those set of disturbances I talked about in a slide or two up earlier. And the idea is that the engineer and the modeling tools are really part of the system. They're not creating a system one pass. You're part of the system, continually looking for optimization of production. Okay. So in doing that, you're faced with information that comes in many different forms, be it changes in demand, changes in components, component quality, material, changes in material quality and so forth, inventories, all sorts of different viewpoints on things that change there. And then finally, something you don't have in the design world is that, in essence, your plant can be like a laboratory. And you can use it to experiment with processes. And so these are some of the things that that in my work I'm trying to leverage. So you can think of that M&S box that I showed there as an analytical framework. We're not actually making analytical frameworks, we're doing the research that enables these things. But if I were to make a framework for solving problems in manufacturing, what would I try to do? One thing is reuse analytical knowledge. I learned something, I want to be able to apply it in as many ways as possible. Be able to characterize problems and compose problems from components, which you do all the time with advanced tools and design engineering. And then there's this idea of the ability to verify the solution to problems at different levels, because there's different levels of detail that certain people are skilled in. You know, you want to build some capability that can be used out in a production facility. You might not be an engineer that's actually using the thing, but below that level, someone should be able to inspect it and say, yeah, that you're applying the tools correctly, that kind of problem, the uncertainty is known and so forth. So that kind of quality is very important. You want to do it in a way that industry would be interested in seeing. So I want to go through, I have 2 slides about requirements, and later on we want to talk about these. We did some work to define requirements for modeling in production environments. So these are just reliability, usability, automaticity. Okay, so that's the basic ideas of smart manufacturing. Now I want to delve into some technical ideas towards enabling some description of our example investigation. So first I want to talk about the metamodel. Let's start with this sterile definition of a metamodel. You know, sometimes people use the word metamodel in surrogate model. I don't think that here. Conceptual model designed, as it says here, to manage population versus that. Like I say, sterile. But I gave this set of slides to undergraduates last summer, and I said, well, forget about that definition. If you see something like that, what would be the meta model of that? And most people can get it. Well, you had something there that there were boxes with names in them, like were the species, or whatever you want to call it. And there were lines between the boxes, right, that are that relationship between one category and the next, right? So the meta model is that, plus some set of rules about how those things go together. Things in taxonomy, you don't have cycles, right? If it's a taxonomy, you probably want the sibling classes to be disjoint. So metamodel is the thing that expresses this about the model, or some class of models. That's a metamodel. So the first reason I'm interested in metamodels is because you use them to manage models. At the very least, it's often the storage form. I put the model onto a disk and bring it back. It's the thing that is used in domain-specific modeling languages. You can look at it that way. Take some basic language, maybe a standard language, and evolve it toward your needs. And then finally, it's just a model in itself that provides conceptualization that might not have existed earlier. So here's an example of how you might use in production these ideas in metamodel. The interesting thing in production is that you have a set of models. Let's say what we're trying to do is define the world of production scheduling. What I would call component viewpoints or component metamodels would you have to bring together to solve problems in production scheduling? Well, you need to know about demand. You need to know about resource instances, right? The individual tools out on the machine tools out on the floor. The resource classes, so that you can talk about the capabilities of things. Generally, you want to associate the capabilities with the classes, right? This turning lathe has a certain horsepower and a certain table size. Process plans and inventory. So, if I were to have 5 component meta models, I could build those things into a problem-solving, something that can solve problems in production scheduling. And this is not all that uncommon. You get the same thing anytime, it seems to me, you look at model. Take a look at finite element analysis. It's a combination of geometry, mesh, loads, and materials. You might have a materials database. You have boundary conditions here. Because as we were talking this morning about singularities, we want some time. Okay, so my next technical thing here is about mapping, and that's closely related to what I'm talking about it with metamodels. Okay, so we can take that metamodel that we looked at earlier, and we can structurally or conceptually map it into some other set of objects that are more useful to our problem solving. So an example of a mapping language is QVP. It's objects. It's based on OMG, UML kinds of ideas. It's lexical language. I'll show you a picture in a second. It's in some ways like Sparkle. In Sparkle, you have this ability to weave together a set of statements by using a variable, the same variable and a number, and then connect them all together. And that's the kind of thing you do with QVP map. I won't go into this kind of detail, but that's kind of what it does. But okay, so here's sort of what I'm calling opportunity number 2 is the idea that you could use metamodels and mapping as a way to just get rid of APIs entirely. If I want to use a program like Cplex, I have 5 different APIs. I can use Python or Ruby or something. So that's a way to get my information into Cplex. But what if instead I just had a meta model? I had a model that conceptualized what Cplex is, and I just wanted to populate that model with a set of truth, facts, and then serialize it as Cplex code. You could do that to so many tools, I think. This is one of my research issues, is to explore this idea. And in some sense, it's more knowledge-based to do that, because you're talking about facts as opposed to operations, which are complex to programmatically put together. It's easier to do rule-based things and add information in a rule-based way than it is to define programmatically programming. If that's making sense to you. We'll talk about that later. Okay, so the third area is domain-specific. Again, very closely related to mapping and metamodels. I define a DSL as a metamodel that mediates between the user viewpoint and a tool. Okay, a tool viewpoint. And for me, the quintessential metamodel, or DSL would be SPICE. Engineer knows very much what he's going to do with SPICE. These tightly focused tools, unlike, say, MATLAB or something. You can do all sorts of things. But you sit down with this LT SPICE tool, and you know just what you can do with it, and you do just that one thing. So, one observation about DSLs that you notice, people who espouse the DSL way of working, is they talk about it as being something they're doing in opposition to more consensus-based models. So, SysML took over a decade to define, and there's still a standing committee, probably a dozen people who get together once a week and talk about how to bring it forward. It's a very useful thing, but it's a lot of work. And trying to get that consensus to say everyone's going to agree that this is what a connector is and this is how connectors work. A lot of industry is not going to find the rationale for getting involved in that is not very compelling to them. So with the DSL, well, it's not based to accommodate all those views. You just do what you need to, and that's some of the value of it. No need for consensus building. Okay, so now I have 4 slides that could have been sidebars in a way. They're just like things I felt that in a talk like this I should mention. And in my project, we like we liked it more at the beginning now, but that's a different issue. It's not a domain-specific model that you can build libraries in. It's open language, equation-based. These are the sorts of things that we seek in solving our problems. The second one of my 4 sidebars here is this idea that with solving problems with metamodels, you don't have just that strata or veneer I talked about earlier, being able to go down to levels of detail. But you also have a dimension, a process kind of dimension, where different people with different skills step in at different times of the development of the problem to do their part. So you have people that are very skilled in the modeling of technology, and you have the application engineer who understands the requirements well. And in solving a problem with metamodels, those guys work closely together and you come up with the domain-specific language and so forth that then in cooperation with the person who's an expert with the tool drives the tool using that domain-specific language. And then, of course, there's the project engineer at the end who wants to use that tool in a production sense. So that's theme number 2. Theme number 3 about these, sidebar number 3 is this idea of compositionality. This is one of the challenges to using metamodels, is the problem of just taking those 4 or 5 models that I illustrated before and putting them together to solve the problem. There could be things in each one of those models that contradict each other, not compatible. I have a different view of how time is measured or something like that. It'd be that simple. You view time as a start and end time, duration of something. I view it as a start time and duration. So resolving problems in compositionality is a challenge that the CPS research is looking at. And I think for reasons we can talk about later, the interesting solutions to that are axiomatic. So I think most graduate students will be familiar with the idea of using metamodels with general problem-solving tools. There's so many papers being written on this kind of stuff now. And it's a powerful way to solve a problem. Start with a metamodel and a SAT solver, SFT solver, DAE solver. All kinds of opportunities. So now I think we're ready to talk about an application of this. So additive manufacturing is a very active research area. General Electric said that by 2020 they're going to produce, I think they said 100,000 additive manufacturing 300 machines, and I'm not talking about maker bot kinds of machines, but metal powered kinds of machines. They're building combustor nozzles and some pretty intense kinds of parts with added manufacturing process. And in doing that, for example, in General Electric, they're going to be faced with issues of getting those things certified through the FAA. So you need to understand pretty well the process and its capabilities so you can convince the FAA that these things belong in airplanes. Like I say, there's a lot of research there. It's not physics-based for the most part. They have empirical models and use design of experiments and so forth to find, to understand these problems. So, in my example problem, as in most of these AM problems, we're going to look at a relationship between some set of explanatory variables, process parameters, and material parameters, and their relationship to some set of outcomes, being like the part density, the surface roughness, tensile strength, and so forth. And the goal of this little sub-project is to first define those unit manufacturing predictive models, and then to use those in optimization, where I have models, for example, for surface roughness and tensile strength and so forth, and I need to find trade-offs between those things by composing equations and coming up with an optimization problem. So how do we solve these problems? Like, as I mentioned, design of experiments is a way to maximize the information obtained from expensive experiments and use simple models. And it's great stuff written just by NIST on the topic that I use quite a bit. So this is just the idea that you start with a black box, right? There's a set of control variables like the scan speed and the laser power that I mentioned earlier, and then there's outputs, which are the surface roughness, tensile strength, and so forth. And here's a flow chart of how you might go about that. You identify what you're trying to achieve with your AM process. Well, I want it to be strong, I want it to be close to the design tolerance dimensionally, and so forth. In solving the problem, you might do some screening experiments to identify the key variables affecting the response. Then you would do some more experiments to define the actual relationship, the regression model that you're going to fit to. Identify the uncertainty in that, and then probably formulate optimizations, which are the trade-offs between those things, right? To actually come up with knowledge that is useful in operational settings. So having done all this, you get to this point, and now you have ideas that you can put into practice as an optimization. So let's think for a second about how that works. Suppose I have 8 factors that I'm interested in. I think that these things affect the surface roughness or tensile strength and so forth. In the experiments, I'm going to take those 8 variables and vary them according to whatever the experimental design is, box banking or something like that. So I'm going to actually be setting the material properties, probably by seeking out a material that has the composition that's needed for that experiment. But in production, typically you wouldn't do that. You get this powder metal from the supplier, and it is what it is. It's supposed to be what you asked for, but you're not going to change it in production. You don't have, let's assume you don't have that capability. You really don't. So in production, the material variables are going to be constraints, and the optimization problem is these are the design variables. You get the design variables and then these things which are going to be constraints. And if you get all that done, you have a tool that's useful for production. So now I'm going to start bringing in some of those ideas of the meta modeling and so forth that I talked about earlier. And So I talked about this control system paradigm, the need for usability, metamodels, composing views, mapping of APIs, and so forth. So maybe you can guess what I'm thinking. Maybe not, but I had this idea that I'd like to treat equations as objects and link those equations with web data that talks about the meaning of a property, so I can do dimensional analysis. I'd like to use production facility, as I suggested, as a lab, experimental lab. I'd like to do the verification with these links to data. I'd like to be able to point to in particular inspection data from the process plan I ran as part of an experiment and bring that data back and say, well, you know, that's the data I got, and I have traceability back to that data by using these by using it or approaching the problem in a web-based way. So strata verification, and then this idea of doing it all in a notebook. Okay, so before I go into the details of that, I'll point out that I know that there's challenges to this that make it difficult. And I'm not going to talk about these 4 things in particular. Maybe we can talk about that later. But equations and web, they don't really fit that well together for various reasons. And when I talk about equations, you almost always talk about equation relative to the tool and solver that it's being used with. So the idea of taking an equation and saying, aha, this is the knowledge about this process that I want to share with the rest of the world is a challenge. So that's, and just the use of the equation as this shared object versus its life inside a model is, there's some challenges. And then there's, of course, the continual challenge of version web data. So I had this idea of doing this with a notebook because notebooks are a nice way to generate engineering reports. But we'd like an engineering report with all this links out to the production facility. So if I do that in an open notebook like IPython, which runs in a web browser, then I can make links to URLs and so forth and bring things in with web services to get the data into doing the problem solving. And of course, Python has lots of nice science libraries that will make that easier. This is not my work, but I just grabbed some IPython notebooks off the web just to see, illustrate some of the things you can do. So you can do drawings and nice math. Put it right in the middle of your work. So in addition to having, I can't really see this. So this part here is Python code, and this is a plot that came out doing that. So the challenge technically is how do you get the experimental data into the notebook, and how do you get the results, the optimizations, and so forth back out. And of course, as suggested, meta-modeling domain-specific languages, and this idea of serializing the meta-model population as input to the tools. I'd like to link information in the analysis with dimensional data in QUDT, which is quantities, units, dimensions, and data types. I think that's what that stands for. It's an ontology of units of measure. And then there's the matter of production data and it coming in from all sorts of ways. So, for example, if I were to run my experiments as process plans, then I could, in those process plans, specify the experimental conditions and reference the quality of the inspection data coming back and keep all that stuff together. So it'd be easy to bring production data into my analysis, environmental generative analysis. Okay. So back to this slide. So now I'll talk about this problem in the context of using it with a notebook. So early on, what I would do is I do some work to register these equation types. And we know that we're just going to use a second order regression formula. Just type that thing out and send it to some place that'll parse it, and break it up into the parts, and then step by step, tell me what those variables are and link those to data types in an ontology that says, okay, this one's laser power. What I mean by the laser power here is maybe the electrical laser, there's an optical laser power, and there's electrical laser power. Maybe this, I'm talking about the electrical laser power here. I'm talking about it in the context of what the manufacturer told me this machine was capable of. It's not a measured value and so forth. So in creating this notebook, an engineering report, I'm linking back to things in the production facility and creating this traceability back to things, while at the same time enabling ways to bring that data into the analysis. So registering equations and variables would be a key part of that. So this is just a spreadsheet of the things that I want to pull together to make that happen. So these would be specified in plan tasks, and these are data coming back from QIF, the Quality Information Framework. So I get some XML data back each time I ran one of these things that would populate that table. So I need a meta model of process, and this is just 1/10 of it here that just says a process plan has plan tasks and task occurrences, which are parts of jobs and so forth. And then going down into the details of the plan task, you get into some interesting data, especially in additive manufacturing. Talking to some of the guys in our additive manufacturing project, it's not just 4 or 5 variables that I talked about, the laser power and so forth. They have about 100 different settings for their machine that you need to check to get these things right. So the definition of a plan task or a manufacturing task can get quite complex, and there can be a whole ontology behind that. Likewise, sometimes there isn't an ontology, it's just like an XML schema. For QIF, I don't have a meta model, but I have this XML schema that I can look at. This is a picture of top-rated composer where I pulled the XML schema and it made it basically a UML model of the thing to show me how it all fits together. So in the next step is I'd run those, having defined the process plans for the Box-Benken sort of designs, I'd run those experiments as jobs out in my production facility and come back with data that would define the coefficients of the response function. So I get models that look like this. Right? So there's one for tolerance and service roughness and so forth. There's beta 0, and looks like there's quadratic terms in there and so forth. So one of the key objects in doing that is equation, and the ability to parse that thing is a key part of this. So I needed a model, a meta model of an equation, and Modelica has one. I found today there's other interesting possibilities there, but from Modelica I can get this notion of equation. It's, you know, the way this is my own meta model, by the way, and it's the style of meta modeling here is really based on the syntax, which sometimes you have to do with parsing something. Yeah.
Wait. Modelica has a grammar.
Yeah, so that's what this is. This is the grammar being instantiated. Okay, so what is and I can look through this and say, I don't know, okay, an equation is consists of the left-hand side consists of a simple expression, which is in the productions of grammar. The simple expression is right there, and it consists of a set of logical expressions. Okay, so in parsing that thing, I'm going to populate all these things, and it gets to be, you know,
Well, you want that part of need. Not necessarily.
it's going to be a lot.
Yeah.
It's going to, it's,
No,
you're
I
gonna-
agree with it, yeah.
you can just
That's
get
a grammar,
down.
that's a grammar, that's what it is, right?
Right, and just to get down into okay, I'm finally at variable x. I created 15 objects to get there. It's, you know, it's this simple expression with something inside of it, with something inside of it, and something inside of it, and so forth. That's how I'm doing it.
We can talk that, I think you can do better.
Yeah, it's quite true. I don't believe I believe you. We can do better than that.
We can do better, for example, how are you going to compute, so you talked about trade-off. So that applies you under optimization.
Right.
So you might want, somewhere along that, you might want to compute partial derivatives.
Yeah, you can't do that with Delca so much, but you know, at this point, I know for my problem, I don't have any partial derivatives. I just have these
I know, I can show
regression
you,
problems.
I can show you something now, so you can do partial derivatives.
Yeah. So for today, this is fine, and I agree. We want to clean this up, but we also need to publish soon. so we're going to get that idea out there. So the next step, if you have these object models of the equations, is to compose them in doing a trade-off study. So you don't want to just optimize for surface roughness. You want to look at surface roughness and trade off relative to tensile strength or something. So in your notebook, you'd like to compose those things into your optimization problem. And in doing that, what I'm doing, we're getting to the part which I haven't implemented yet, so I'm going to just tell you how I think it works. And that is, use QVT to map the equation models into a metamodel of the OPL language. It's an optimization language for C-plex. So I have multiple equations, and I have a template that says, the template will contextualize the mapping to say, this is the kind of mapping we do for a design of experiment kinds of things. You tell me what the constraints are, you tell me what the equations are, I can map those things into C-plex. Okay, so what I've achieved here, let's talk first about the so the second goal is to build that optimization as a composition of equations. So what I've achieved through doing this equations of object thing is to look at problems outside of the tool and try to raise the level of the knowledge that was embedded in the tool out to a broader context where that can be talked about in engineering reports and manipulated, pulled into ad hoc analyses in the process of doing that. So that's sort of one of the research questions. I think there's probably value in talking about the notebook as this enterprise linked thing. So that's another aspect of this. And then the details of using the population and template to step away from APIs is another issue. That's could be the key research contribution here is just to suggest to people that we're going to move forward in higher levels of complexity of compositionality. The way to do it is to get away from these APIs and use a more knowledge-based way of putting information together. So that's pretty much it. So I tried to illustrate this idea of the control system paradigm, the idea of using the word data with metamodels and models. The idea that the analytical framework is not the center of the world, because you see a lot of research out there that says, well, you know, if I can only put all this information into the form I need for analysis, if the world would just be the way I want it, I can do this analysis very nicely. But it doesn't work that way in the real world because that data is out there. It's standards-based for some reason. It's not quite in the form you want. You need to know about the assumptions about the data. So in doing work in this area, you need to get used to the sense of not being the center of the world, but being able to cope with these different ways of representing things in different competing needs. So there's other things, other projects I didn't talk about. I talked about the Python one, but we have some work in production schedule, and so maybe some standards work in coming up with a meta-modeling framework that industry, that may be a few years off. So that's it.